Close your eyes for just a moment. Imagine drifting through a world where the laws of physics bend, where you can fly without wings, where people you've never met feel like old friends, and where the impossible becomes ordinary. Every night, without fail, your brain creates these elaborate realities, weaving stories so convincing that you forget you're asleep at all. We spend roughly 1/3 of our lives in this mysterious state, yet the sleeping mind remains one of science's most captivating puzzles. Welcome to Bedtime Biology, where science meets serenity. Each night, we explore the quiet wonders of the natural world, calming your mind and sparking your curiosity. Please like, subscribe, and comment below with where you're checking in from. Tonight, we're venturing into the landscape of sleep itself, where memories transform, where learning deepens, and where consciousness takes on forms we're only beginning to understand. We'll explore the intricate architecture of sleep, the enigmatic world of dreams, and the remarkable ways your brain uses the night to prepare for tomorrow. From the molecular mechanisms that consolidate your memories to the master clock that governs your daily rhythms, from the haunting persistence of nightmares to the strange phenomenon of lucid dreaming, we'll journey through the sleeping mind in all its complexity. So, settle in, let the day's worries fade, and prepare to discover what really happens when you close your eyes and drift away. Sleep is not a single uniform state, but rather a carefully orchestrated progression through distinct stages, each with its own signature pattern of brain activity and its own purpose in maintaining our health and well-being. When you first close your eyes and begin to relax, your brain doesn't simply switch off like a light. Instead, it embarks on a cyclical journey that will repeat multiple times throughout the night, each cycle lasting roughly 90 to 120 minutes. The journey begins with stage 1 of non-rapid eye movement sleep, or NREM sleep. This is the lightest stage, a transitional phase between wakefulness and true sleep. If you've ever felt yourself drifting off while sitting in a comfortable chair, only to jerk awake with a sudden muscle spasm, you've experienced stage 1 sleep. These hypnic jerks, as they're called, are completely normal and occur as your muscles begin to relax. During this stage, which typically lasts only 5 to 10 minutes, your eyes move slowly beneath your closed eyelids, your heart rate begins to slow, and your breathing becomes more regular. Your brain waves, measured by electroencephalography, shift from the relatively fast and irregular alpha waves of relaxed wakefulness to slower theta waves. It's remarkably easy to wake someone from stage 1 sleep. A gentle touch, a quiet sound, or even the shifting of light in the room can bring them back to full alertness. Yet even in this lightest stage of sleep, the brain is beginning its nightly work. The boundary between wakefulness and sleep becomes fuzzy. You might experience fleeting thoughts or images, fragments that feel dreamlike but lack the narrative structure of true dreams. Some people report sensations of falling, or of floating, or of sudden insights that seem profound in the moment but vanish upon waking. As you descend deeper into sleep, you enter stage 2 NREM sleep. This is where most of your night will be spent, accounting for about 45% of your total sleep time. Stage 2 is characterized by continued slowing of your heart rate and a drop in body temperature as your body prepares for the deeper sleep to come. Your eye movements stop entirely and your muscles relax further, though they're not yet in the state of near paralysis that will come during REM sleep. The most distinctive features of stage 2 sleep are visible only to those monitoring brain activity. Two specific patterns emerge in the electrical signals: sleep spindles and K complexes. Sleep spindles are brief bursts of rapid brain activity, lasting just half a second to 3 seconds, occurring every 3 to 6 seconds. These spindles are thought to play a crucial role in memory consolidation, helping to transfer information from short-term storage to long-term memory. They also appear to protect sleep from disruption, helping to block out external stimuli that might otherwise wake you. K complexes are sudden, high-amplitude waves of electrical activity that last just a second or two. They too seem to play a protective role, helping to maintain sleep in the face of potential disturbances. But they may also be involved in memory processing, serving as markers of the brain's offline work of organizing and integrating new information with existing knowledge. During stage 2 sleep, you're genuinely asleep, though you can still be awakened relatively easily. The first episode of stage 2 sleep in a night typically lasts 10 to 25 minutes, but these periods grow longer as the night progresses. After moving through stage 2, you descend into stage 3, also known as deep sleep or slow wave sleep. This is the most restorative stage of sleep, the time when your body does its most intensive repair work. Stage 3 is characterized by the presence of delta waves, the slowest and highest amplitude brain waves. These long, rolling waves give this stage its alternative name, slow wave sleep. During deep sleep, your heart rate and breathing slow to their lowest points. Your blood pressure drops. Your muscles are deeply relaxed. It's difficult to wake someone from stage 3 sleep, and if they are awakened, they often feel disoriented and groggy, a state called sleep inertia that can last for 30 minutes or more. This grogginess isn't just mental fog. During sleep inertia, cognitive performance is genuinely impaired, sometimes more so than during acute sleep deprivation. Deep sleep is when growth hormone is released, promoting cell repair and tissue growth. It's when your immune system is strengthened, when your body builds bone and muscle, and when energy is restored for the coming day. Without adequate deep sleep, you wake feeling unrefreshed, no matter how many hours you spent in bed. Infants and children spend much more time in deep sleep than adults, which makes sense given their rapid growth and development. As we age, the amount of time we spend in deep sleep gradually decreases. An adult might spend about 20 to 25% of the night in stage 3 sleep, but an elderly person might spend half that amount or less. The distribution of deep sleep across the night is not random. Most of your slow wave sleep occurs in the first half of the night, in the first few sleep cycles. This is why the advice to get your sleep in during the early hours has some scientific merit. If you stay up late and try to compensate by sleeping in, you might get the same total hours of sleep, but you'll have missed the window when deep sleep is most prevalent. After progressing through the 3 stages of NREM sleep, something remarkable happens. Rather than continuing into even deeper sleep, your brain begins to become more active. Your heart rate quickens. Your breathing becomes more rapid and irregular. Your eyes begin to move rapidly back and forth beneath your closed lids. You have entered REM sleep, the stage most closely associated with vivid dreaming. REM sleep is paradoxical. Your brain activity during REM resembles that of wakefulness in many ways. If you were to look at an EEG recording of someone in REM sleep, you'd see fast, desynchronized brainwaves, similar to those seen when someone is awake and alert. Yet, the sleeper is profoundly unconscious, typically harder to wake than during stage 2 sleep. This combination, brain activity suggesting wakefulness coupled with deep sleep, is why REM is sometimes called paradoxical sleep. The most distinctive feature of REM sleep is the rapid eye movements that give it its name. These quick, darting movements occur in bursts throughout the REM period and are thought to correspond to the visual imagery of dreams. Interestingly, people who are blind from birth still experience REM sleep and rapid eye movements, even though their dreams don't contain visual imagery, suggesting that the eye movements are a core feature of this sleep stage, rather than simply a response to dream content. Perhaps the most striking characteristic of REM sleep is muscle atonia, a temporary paralysis of most voluntary muscles. Only the diaphragm, allowing you to breathe, and the muscles controlling eye movement remain active. This paralysis appears to be a protective mechanism, preventing you from physically acting out your dreams. In rare disorders where this paralysis fails, people can indeed act out their dreams, sometimes with dangerous consequences. REM sleep occurs cyclically throughout the night, with the first REM period typically beginning about 90 minutes after you fall asleep. This first REM period is brief, often lasting only 10 minutes. But as the night progresses, REM periods become longer and more intense. The final REM period of the night, occurring in the early morning hours, can last up to an hour. This is why we often wake from dreams, why our most vivid and memorable dreams occur toward morning, and why being awakened suddenly can interrupt complex dream narratives. REM sleep makes up about 20 to 25% of an adult's total sleep time, though this percentage varies considerably across the lifespan. Newborns spend about 50% of their sleep time in REM, a proportion that gradually decreases through childhood. By adolescence, the proportion of REM sleep has fallen to adult levels. In late adulthood, both the amount and intensity of REM sleep decline further, though not as dramatically as the decline in deep sleep. The functions of REM sleep are still being unraveled, but research strongly suggests it plays crucial roles in memory consolidation, particularly for procedural memories and emotional processing. REM sleep appears to be essential for integrating new experiences with existing knowledge, for emotional regulation, and for the development and maintenance of neural connections. When people are selectively deprived of REM sleep, they show what's called REM rebound, spending more time in REM on subsequent nights, as if the brain is trying to make up for lost time. A complete sleep cycle, from stage 1 through stage 3 and back through REM, takes about 90 to 120 minutes on average, though there's considerable individual variation. Most people go through 4 to 5 complete cycles in a typical night's sleep. The cycles aren't identical. The first cycles of the night contain more deep sleep and less REM. As the night progresses, the amount of deep sleep decreases and REM periods become longer and more intense. This ultradian rhythm, this recurring 90-minute cycle, doesn't stop when you wake up. Some researchers believe we continue to cycle through periods of higher and lower alertness throughout the day, roughly every 90 to 120 minutes. You might notice times when you feel more focused and energized, followed by periods when your attention wanes and you feel the urge to rest. These fluctuations may be echoes of the same biological rhythm that structures your sleep. the architecture of sleep changes throughout life in predictable ways. Newborns have very different sleep patterns from adults, sleeping in shorter bursts throughout the day and night, with sleep and wake states less clearly differentiated. They also enter sleep through REM rather than through NREM, a pattern that reverses in early childhood. As children grow, their sleep becomes increasingly concentrated in the nighttime hours, and the proportion of time spent in each sleep stage shifts toward the adult pattern. Teenagers often struggle with early school start times, not due to laziness, but because of a genuine shift in their circadian rhythms during puberty. Their natural sleep-wake cycle tends to shift later, a phenomenon sometimes called sleep phase delay. This biological change means teenagers naturally feel alert later in the evening and want to sleep later in the morning than younger children or adults. In older adults, sleep architecture changes again. Total sleep time may decrease slightly, but more noticeably, the quality of sleep changes. Older adults spend less time in deep sleep and experience more frequent awakenings during the night. REM sleep decreases as well, though not as dramatically as deep sleep. These changes are partly due to changes in the brain regions that regulate sleep, partly due to medical conditions that become more common with age, and partly due to medications that can interfere with sleep architecture. Understanding sleep architecture helps explain why not all sleep is created equal. You can spend 8 hours in bed, but still feel exhausted if those hours were filled with frequent awakenings and little deep or REM sleep. Conversely, a well-structured 6 hours of sleep containing good proportions of all sleep stages might leave you more refreshed than a poorly structured 8 hours. The measurement of sleep architecture requires polysomnography, a comprehensive recording of brain waves, eye movements, muscle tone, heart rhythm, and breathing during sleep. In research settings and sleep clinics, this detailed monitoring reveals the intricate dance your brain performs each night, the precise timing of transitions between stages, and the disruptions that might be interfering with sleep quality. But even without such monitoring, you can often sense the quality of your sleep based on how you feel upon waking. That feeling of being truly rested, of waking refreshed and alert, typically reflects a night of well-structured sleep, with adequate amounts of each stage. The science of dreams have captivated humanity since the dawn of consciousness itself. Ancient civilizations believed dreams were messages from gods or glimpses into the future. Some cultures saw them as journeys of the soul during sleep. Even now, in our age of neuroscience and brain imaging, dreams retain an air of mystery and fascination that few other mental phenomena can match. The simple question of when we dream has a more complex answer than you might expect. For decades, it was believed that dreams occurred exclusively during REM sleep. This made intuitive sense. REM sleep, with its rapid eye movements and brain activity resembling wakefulness, seemed the natural home for the vivid, bizarre narratives we call dreams. Early research supported this view. When people were awakened during REM sleep, they reported dreams roughly 80% of the time. When awakened during NREM sleep, dream reports were much less common. But as research techniques became more sophisticated, this tidy picture began to blur. It turns out that we do dream during NREM sleep, just differently. NREM dreams tend to be shorter, less vivid, less bizarre, and less emotionally intense than REM dreams. They're more like thoughts than full-fledged dreams, more fragmented and less narrative. Still, they're definitely there, especially during the later stages of NREM sleep. When awakened from stage 2 or stage 3 sleep, people report some form of mental activity about 50 to 60% of the time. The most vivid and memorable dreams, the ones we typically think of when we use the word dream, do primarily occur during REM sleep. These dreams have a narrative structure, however illogical. They unfold over time, with you as a character in the story. You interact with dream characters, you move through dream spaces, you experience emotions that can range from pure joy to absolute terror. The dream world feels convincingly real while you're in it, even when it violates every law of physics and logic. REM dreams engage multiple brain regions in ways that create this rich, immersive experience. The visual cortex is highly active, generating the imagery that fills your dreams. The limbic system, particularly the amygdala, is intensely activated, which may explain why dreams are often so emotionally charged. The hippocampus, crucial for memory formation, is active during dreams, though in a different way than during waking. Meanwhile, the prefrontal cortex, responsible for logical thinking, planning, and self-awareness, shows decreased activity. This prefrontal hypoactivity might explain why dreams feel so logical and reasonable while we're experiencing them, only to seem bizarre and nonsensical when we remember them after waking. The content of dreams varies enormously from person to person and from night to night. Some dreams are mundane, replaying events from the day or minor variations on familiar themes. Others are surreal and symbolic, filled with impossible events and transforming characters. Some dreams are so vivid they feel more real than waking life. Others are vague and fragmentary, dissolving upon waking like smoke. Despite this variation, certain themes appear consistently across cultures and individuals. Many people dream of falling, of being chased, of showing up unprepared for an important event, of losing teeth, or of discovering new rooms in familiar buildings. These common dream themes might reflect universal human anxieties and experiences, though their specific meanings, if any, remain subjects of debate. Dreams often incorporate elements from recent waking experiences, a phenomenon researchers call day residue. If you spend the day learning a new skill or dealing with a stressful situation, elements of that experience may appear in your dreams that night. But dreams don't simply replay events. Instead, they remix and recombine elements in novel ways, blending recent experiences with older memories, with current concerns, and with entirely fabricated scenarios. The question of why we dream has spawned numerous theories, none of which has achieved universal acceptance. Each theory captures some aspect of dreaming, yet none seems to fully explain this complex phenomenon. Sigmund Freud, in his groundbreaking work, The Interpretation of Dreams, proposed that dreams are the royal road to the unconscious, revealing hidden wishes and conflicts. According to Freud, the manifest content of dreams, what we actually experience and remember, disguises latent content, the true unconscious wishes and desires that we cannot acknowledge while awake. A dream about climbing a tower in Freudian interpretation might symbolize something else entirely, something too threatening to express directly even in the privacy of sleep. While Freud's specific interpretations have largely fallen out of favor in neuroscience, his core insight that dreams might serve psychological functions remains influential. Carl Jung, Freud's contemporary and later critic, offered a different perspective. He believed dreams didn't disguise meaning, but expressed it directly through a language of symbols and archetypes, universal to human experience. For Jung, dreams were the psyche's way of communicating with the conscious mind, offering insights and guidance. Modern neuroscience has moved away from these psychoanalytic approaches, seeking instead to understand dreams in terms of brain function and evolution. One prominent theory, the activation synthesis hypothesis, proposed by Alan Hobson and Robert McCarley in the 1970s, suggested that dreams are essentially the brain's attempt to make sense of random neural activity. During REM sleep, the brainstem generates bursts of electrical activity that propagate through the brain. The cortex, always trying to create coherent narratives from whatever input it receives, synthesizes these random signals into a dream. In this view, dreams have no inherent meaning. They're just noise that the brain weaves into stories. While elegantly simple, the activation synthesis hypothesis struggles to explain several aspects of dreaming. If dreams are just random noise, why do they so often incorporate emotionally significant content? Why do they sometimes rehearse skills we've been learning? Why do people with similar concerns and experiences often have similar dreams? A more recent theory, the threat simulation hypothesis, proposed by Antti Revonsuo, suggests that dreaming evolved as a way to rehearse responses to threatening situations. During REM sleep, the amygdala, which processes fear and other emotions, is highly active. Dreams often feature threatening scenarios, being chased, falling, confronting dangerous animals or hostile people. Perhaps, Revonsuo argues, dreams serve as a kind of evolutionary training simulator, allowing our ancestors to practice fight or flight responses in the safety of sleep. Those who were better at simulating and responding to threats in their dreams might have had survival advantages in waking life. This theory explains the prevalence of negative emotions and threatening scenarios in dreams, but it struggles with dreams that are mundane, pleasant, or utterly bizarre. Not all dreams involve threats, and many involve scenarios that would have had no adaptive value for our ancestors. Matthew Walker, a prominent sleep researcher, has proposed that REM dreams serve an important function in emotional regulation. He notes that noradrenaline, a stress hormone associated with anxiety, is nearly absent from the brain during REM sleep. Meanwhile, brain regions involved in processing emotions and memories are highly active. Walker suggests that REM sleep and the dreams that occur during it allow us to process emotional experiences in an environment free from the neurochemical signature of stress. We reactivate emotional memories, but in a calmer state, which may help us come to terms with difficult experiences and reduce their emotional charge. Supporting this theory, research has shown that people deprived of REM sleep show decreased ability to recognize and respond to emotional cues in others' faces. They also show impaired emotional regulation and are more reactive to negative stimuli. Furthermore, people with mood disorders like depression often show abnormalities in their REM sleep, suggesting a link between REM, dreaming, and emotional well-being. Another perspective, the memory consolidation theory, proposes that dreams are a side effect of the brain's memory processing during sleep. During the day, you accumulate vast amounts of information and experience. During sleep, particularly during REM and the transition into REM, your brain reviews these experiences, deciding what to keep, what to discard, and how to integrate new information with existing knowledge. Dreams, in this view, are glimpses of this memory consolidation process. Fragments of memories being replayed, reorganized, and integrated. The bizarre quality of dreams might result from the brain making unexpected connections between disparate memories. This theory is supported by the observation that dreams often feature memory fragments from recent experiences combined in novel ways. It's also consistent with evidence that sleep, especially REM sleep, is crucial for memory consolidation. However, it leaves open the question of why this memory processing needs to produce conscious experiences at all. Why not just process memories unconsciously? Eric Holl has proposed a more recent theory called the overfitted brain hypothesis. In machine learning, overfitting occurs when a model becomes too closely tailored to its training data, performing well on familiar examples, but failing to generalize to new situations. Howell suggests the brain faces a similar challenge. During waking hours, your brain continually learns from experience, forming strong associations based on what you encounter. But if learning is too precise, too fitted to specific experiences, you might lose the ability to generalize and respond flexibly to new situations. Dreams, Holl proposes, help prevent this overfitting by exposing the brain to experiences that are similar to, but not identical to, waking experiences. The strange, recombinatorial nature of dreams, mixing familiar elements in novel ways, might help maintain the brain's ability to generalize and adapt. It's similar, he suggests, to how machine learning systems are trained on slightly corrupted or varied data to improve their performance. In this view, the bizarreness of dreams isn't a bug, but a feature, essential to their function. Most recently, research by David Eagleman has proposed that dreams might serve to protect the visual cortex from being taken over by other sensory systems during the night. The brain is remarkably plastic, constantly reorganizing itself based on input. When you sleep, you're not receiving visual input for hours. Without some form of stimulation, other sensory modalities like hearing or touch might begin colonizing visual processing areas. Dreams, particularly the vivid visual imagery of REM dreams, might keep the visual cortex active and prevent this takeover. Supporting this theory, research shows that people who are born blind and never have visual experiences don't have visual dreams, though they still experience REM sleep. Each of these theories captures something important about dreams, yet none seems complete on its own. The truth is likely that dreams serve multiple functions. They may help with emotional regulation while also contributing to memory consolidation. They might prevent overfitting while also protecting sensory processing areas. Evolution is an opportunistic tinkerer, and a brain state as universal and ancient as REM sleep has likely been co-opted for multiple purposes. What we do know is that dreaming is not optional. When people are deprived of REM sleep specifically, by being awakened whenever they enter REM, they show REM rebound, spending much more time in REM when finally allowed to sleep undisturbed. The brain seemed to defend REM sleep and the dreams that accompany it, suggesting that whatever functions dreaming serves, they're important enough that the brain won't give them up without a fight. The scientific study of dreams has been revolutionized by advances in brain imaging and by the discovery that lucid dreamers can communicate with researchers during REM sleep through pre-arranged eye movement signals. These techniques have allowed researchers to correlate specific dream contents with patterns of brain activity to understand which brain regions are involved in different aspects of dreaming, and to begin unraveling the neural basis of this most mysterious of mental states. Yet, for all our advances, much about dreams remains enigmatic. We still don't fully understand why dreams take the bizarre forms they do, why some people remember their dreams vividly, while others rarely recall dreaming at all, or why certain themes and symbols appear so consistently across different cultures and individuals. Dreams remain, as they have always been, one of consciousness's greatest mysteries, a nightly reminder that the mind contains depths we're only beginning to chart. Memory and the sleeping brain. If you've ever pulled an all-nighter studying for an exam, you've probably experienced the frustration of finding that facts you thought you knew seem to have slipped away. You might have felt that staying awake to cram was necessary, but your brain had other ideas. It turns out that sleep, far from being time stolen from productive study, is actually when much of the real work of memory formation occurs. Memory is not a single thing, but a collection of different types of memories, each processed and stored somewhat differently by the brain. Declarative memories are facts and events you can consciously recall, like remembering what you had for breakfast, or knowing that Paris is the capital of France. These break down further into episodic memories, memories of specific events from your own life, and semantic memories, general knowledge about the world. Procedural memories, in contrast, are skills and habits, things you know how to do but might struggle to explain in words, like riding a bicycle or typing on a keyboard. The formation of any lasting memory involves three basic processes. First is encoding, the initial learning or experiencing of something new. This happens while you're awake and paying attention. If you don't encode information in the first place, there's nothing for sleep to work with. Second is consolidation, the process by which memories become stable and resistant to interference. This is where sleep plays its most crucial role. Third is retrieval, the ability to access the memory when you need it later. The traditional story of memory consolidation involves two key brain structures, the hippocampus and the neocortex. The hippocampus, a seahorse-shaped structure deep in the brain, is essential for initially encoding memories, particularly episodic memories. When you experience something new, neurons in your hippocampus become active in patterns that represent that experience. These patterns are initially fragile, easily disrupted by new experiences or by the passage of time. But the hippocampus has limited capacity. It can't store everything indefinitely. Think of it as a temporary holding area, a buffer for recent experiences. For memories to become truly long-lasting, they need to be transferred to the neocortex, the wrinkled outer layer of the brain where long-term memories are stored in a more distributed, stable form. This transfer doesn't happen instantly. It takes time, unfolding over hours, days, or even years. And crucially, it depends heavily on sleep. This process is called systems consolidation, distinguishing it from cellular consolidation, which involves strengthening connections between individual neurons and can occur more rapidly. Systems consolidation is the gradual reorganization of memory representations, their integration into existing knowledge networks, and their transformation from hippocampus dependent to hippocampus independent. During sleep, particularly during slow-wave sleep, something remarkable happens. The hippocampus spontaneously replays patterns of activity that occurred during waking experiences. If you spent the afternoon learning to navigate a new route through your neighborhood, neurons in your hippocampus that were active during that learning will become active again during subsequent sleep, firing in the same sequence but much faster. This replay is not random. It's structured, repeating the learned patterns dozens or hundreds of times. This neural replay is thought to be crucial for memory consolidation. As the hippocampus replays recent experiences, it communicates with the neocortex through coordinated patterns of brain activity. 3 key oscillations seem to orchestrate this communication. Slow oscillations, which originate in the neocortex and reflect the alternation between active and inactive states of neurons during deep sleep. Sleep spindles, rapid bursts of activity generated by interactions between the thalamus and cortex. And sharp wave ripples, brief, high-frequency bursts of activity in the hippocampus that occur during replay. These 3 oscillations don't occur independently. Instead, they're nested within each other in a precise temporal pattern. Hippocampal replay, marked by sharp wave ripples, tends to occur during the active phase of cortical slow oscillations. Sleep spindles also cluster during these active phases. This temporal coordination is thought to create optimal conditions for the hippocampus to teach the neocortex about recent experiences. Each time the hippocampus replays an experience, it strengthens the connections in the neocortex that represent that experience in a more stable, distributed form. Gradually, over multiple replay events across multiple nights, the memory becomes less dependent on the hippocampus and more firmly embedded in cortical networks. The episodic memory, initially rich in specific details about when and where something happened, often transforms into more semantic, generalized knowledge. Different types of memories appear to be consolidated preferentially during different stages of sleep. Declarative memories, particularly episodic memories, seem to benefit most from slow-wave sleep, which dominates the first half of the night. Studies have shown that if you learn a list of word pairs and then sleep, you'll remember them better than if you stay awake for the same amount of time. But if you're specifically deprived of slow-wave sleep, while being allowed to experience other sleep stages normally, this benefit is reduced. Procedural memories, skills, and habits seem to depend more on REM sleep and Stage 2, Sleep for Consolidation. If you practice a finger-tapping sequence or a visual discrimination task, your performance often improves after sleep, even without additional practice. This offline learning, this improvement that occurs during sleep itself, is reduced if you're deprived of REM sleep. The improvement seems to involve both the stabilization of what you've learned and the discovery of hidden patterns or rules that weren't apparent during initial learning. The molecular mechanisms underlying these sleep-dependent changes are beginning to be understood. During sleep, levels of certain neurotransmitters change dramatically. Acetylcholine, high during waking and REM sleep, drops to very low levels during slow-wave sleep. This shift may be crucial for consolidation. High acetylcholine levels during waking are associated with encoding new information. Low levels during slow-wave sleep may allow the brain to shift to a consolidation mode, where new information can be integrated with existing memories without interference from ongoing encoding of new experiences. Various genes and proteins involved in synaptic plasticity also show sleep-wake differences in expression. Some genes that promote the growth and strengthening of synaptic connections are more active during sleep. Others that might interfere with consolidation or that are involved in breaking down synaptic connections are relatively suppressed. These molecular changes help reshape the brain's connectivity, strengthening some connections while weakening others, sculpting the neural networks that store memories. Research using targeted memory reactivation has provided some of the most compelling evidence for sleep's role in memory consolidation. In these studies, researchers pair learning with specific cues, often sounds or odors. A person might learn the locations of various objects, while a specific sound plays each time they learn about a particular object. Then, during subsequent sleep, some of those sounds are played again, quietly enough not to wake the person. The memories associated with the replayed cues show better retention than memories that weren't cued during sleep, suggesting that the cues trigger memory replay and consolidation. Even more remarkably, targeted memory reactivation can be used to bias which memories are strengthened. If you learn two overlapping pieces of information that create some interference with each other, cueing one during sleep will strengthen that memory at the expense of the competing memory. This selectivity suggests that sleep doesn't simply strengthen all recent memories indiscriminately, but can prioritize certain memories based on various factors, including whether they've been recently reactivated. The benefits of sleep for memory aren't limited to consolidation. Sleep before learning also appears to be important for preparing the brain to form new memories. The hippocampus has limited capacity. As you go through the day accumulating experiences, the hippocampus gradually becomes saturated with recent information. Sleep, particularly slow-wave sleep, appears to clear out this temporary buffer, making space for new encoding the next day. Studies have shown that people who are sleep-deprived before learning show reduced activity in the hippocampus during encoding and poorer memory formation. It's as if the hippocampus has become less responsive, less able to form new memory traces. A nap before learning can partially restore this capacity. One study found that people who napped before an afternoon learning session were able to encode information just as effectively as in a morning session, while people who didn't nap showed declining learning ability as the day progressed. This preparatory function of sleep may involve synaptic downscaling, a controversial but increasingly supported theory. The idea is that throughout the day, as you learn and experience, synaptic connections throughout the brain become potentiated, strengthened. If this process continued indefinitely, synapses would become saturated, unable to strengthen further. Sleep, according to the synaptic homeostasis hypothesis, is a time when synaptic strengths are globally downscaled, reduced back to a baseline level. This downscaling doesn't erase memories. It resets the system, making room for new learning while preserving the relative differences in strength between synapses that encode information. Evidence for synaptic downscaling comes from multiple sources. Measurements of synaptic size and strength show decreases from before sleep to after sleep. Brain waves during sleep show patterns consistent with weakening of synaptic connections. And computational models suggest that some form of synaptic downscaling may be necessary to maintain the brain's ability to learn continuously. However, synaptic downscaling seems to be selective rather than global. Not all synapses are weakened equally during sleep. Synapses that were recently potentiated through learning or that encode important information appear to be protected from downscaling. This makes sense. You want to clear out the noise, the unimportant synaptic changes that occur during the day, while preserving the signal, the changes that represent meaningful learning. The interplay between synaptic strengthening through replay and consolidation, and synaptic downscaling for homeostasis, may seem contradictory, but it's likely that both processes occur during sleep, perhaps in different brain regions or at different times of night. Early night, dominated by slow-wave sleep, may be particularly important for consolidation and the strengthening of specific memories. Late night, with more REM sleep and lighter sleep, may involve more downscaling. The precise details are still being worked out, but it's clear that sleep is far from a passive state for memory. It's an active, carefully orchestrated time of memory processing. The importance of sleep for memory has practical implications. Students who cram all night before an exam, sacrificing sleep in favor of study time, are working against their own brain's needs. They may be able to hold information in temporary memory long enough to take the test, but that information is unlikely to consolidate into lasting knowledge. Distributing study over several days with good sleep after each study session is far more effective for long-term retention. Similarly, learning a new skill benefits from practice distributed over time with sleep in between. Musicians, athletes, and anyone learning a motor skill will improve faster with regular practice sessions separated by sleep than with marathon practice sessions that cut into sleep time. The skill learning that happens offline during sleep is a crucial part of the learning process, not a luxury. The relationship between sleep and memory is bidirectional. Not only does sleep help consolidate memories, but memories can also influence sleep. When you learn something new and challenging, you often experience more slow-wave sleep the following night, as if your brain is sensing the need for enhanced consolidation. Conversely, conditions that impair sleep, like stress, anxiety, or sleep disorders, also tend to impair memory formation, creating a vicious cycle where poor sleep leads to poor memory, which may create more stress, leading to even poorer sleep. Understanding sleep's role in memory has become increasingly important as our society has become chronically sleep-deprived. The pressures of modern life, the intrusion of artificial light and screens into evening hours, and the cultural valorization of working long hours at the expense of sleep, have created a situation where many people operate in a state of chronic sleep debt. The costs of this debt include not just fatigue and irritability, but genuine cognitive impairment, including deficits in memory formation and consolidation that can affect everything from academic performance to job productivity to quality of life. Learning while we sleep. The phrase, "learn while you sleep," often conjures images of subliminal audio tapes promising to teach you a foreign language or reprogram your subconscious while you slumber peacefully. Those products, despite their appealing promises, don't work. You can't simply absorb new information while sleeping, at least not in any meaningful sense. But the relationship between sleep and learning is far more fascinating and substantial than any dubious self-help product. Sleep doesn't allow you to learn entirely new things without effort, but it is absolutely essential for transforming the fragile traces of daytime learning into lasting knowledge and skills. The process begins with what sleep researchers call encoding, the initial formation of a memory trace while you're awake. This stage requires attention and consciousness. You cannot encode new information while truly asleep. But once you've encoded something, even if that encoding is incomplete or weak, sleep gets to work transforming it. Brain plasticity, the ability of neural connections to change in response to experience, is fundamental to all learning. When you learn something new, whether it's a fact, a skill, or an experience, the pattern of connections between neurons in your brain changes. Some connections grow stronger, others weaken, and new connections may form. These physical changes in the brain's wiring are what allow you to remember what you've learned. Sleep, it turns out, is not just permissive of plasticity, but actively promotes it. Multiple studies have shown that sleep after learning leads to more robust and lasting changes in neural connectivity than staying awake for the same duration. At the molecular level, sleep appears to activate signaling pathways that strengthen synaptic connections. Proteins that are crucial for synaptic plasticity, like brain-derived neurotrophic factor, show increased production during sleep. Genes involved in synaptic growth and restructuring are upregulated during sleep stages associated with memory consolidation. The specific mechanisms vary by brain region and by type of learning. In the hippocampus, crucial for forming new episodic memories, sleep appears to facilitate the transformation of early long-term potentiation, a relatively unstable form of synaptic strengthening, into late long-term potentiation, which is more permanent and depends on protein synthesis. Without sleep, this transition is impaired. The synaptic changes induced by learning begin to decay, and the memory trace weakens rather than strengthens. In motor cortex and other regions involved in skill learning, sleep appears to trigger reorganization of neural representations. When you first learn a motor skill, like typing or playing a musical instrument, the movements are controlled consciously and deliberately by a network of brain regions, including prefrontal cortex and parietal areas. With practice, and especially with sleep after practice, control of the skill gradually shifts to more automatic motor areas and becomes smoother and less cognitively demanding. This reorganization, this transition from controlled to automatic processing, depends critically on sleep. Experimental evidence for sleep's role in skill learning comes from numerous studies. In one classic experiment, participants learned a sequence of finger movements, pressing keys in a specific order as quickly and accurately as possible. Immediately after learning, their performance plateaued, but after a night of sleep, their speed and accuracy improved substantially, even without additional practice. This offline learning, improvement during sleep, was specific to the learned sequence. Performance on a different sequence didn't improve, ruling out general effects of reduced fatigue. Interestingly, the improvement correlated with the amount of stage 2 non-REM sleep, and with the number of sleep spindles, those brief bursts of brain activity characteristic of stage 2 sleep. People who had more spindles showed greater improvement. Furthermore, when sleep spindles were experimentally enhanced using transcranial magnetic stimulation, learning was improved. This suggests that spindles aren't just markers of sleep, but actively contribute to the consolidation of skill memories. REM sleep also appears to contribute to procedural learning, though its role may be different from that of non-REM sleep. Some studies suggest that REM sleep is particularly important for extracting general rules or patterns from learned material, a process sometimes called abstraction or gist extraction. When you learn a complex task, you're not just memorizing specific responses, but also learning underlying patterns and principles. REM sleep may help you discover these patterns, enabling you to generalize what you've learned to new situations. For declarative learning, learning of facts and events, slow-wave sleep appears most crucial. In studies where participants learn word pairs or spatial locations before sleep, retention is strongly correlated with the amount of slow-wave sleep obtained. When slow-wave sleep is disrupted without fully waking the person, using subtle auditory tones that fragment deep sleep, subsequent memory is impaired, even though total sleep time is unchanged. The temporal coordination of brain rhythms during slow-wave sleep seems particularly important. As mentioned earlier, slow oscillations, sleep spindles, and hippocampal ripples occur in a nested pattern, with spindles and ripples clustering during the active phase of slow oscillations. Disrupting this coordination, even while leaving the individual oscillations intact, impairs memory consolidation. It's not just about having these rhythms present, but about having them properly synchronized. Recent experiments have gone beyond simply observing sleep's effects on memory to actively manipulating memory consolidation during sleep. In addition to targeted memory reactivation using sensory cues, researchers have used electrical stimulation to enhance slow oscillations and found improvements in memory retention. Slow, rhythmic transcranial stimulation applied during early night sleep, when slow-wave sleep dominates, can strengthen the amplitude of slow oscillations and enhance the memory benefits of sleep. This has raised the tantalizing possibility of using sleep enhancement techniques to boost learning and memory in practical settings. Could students use devices that enhance slow-wave sleep before exams? Could rehabilitation patients use sleep interventions to accelerate recovery of motor function after stroke? These applications are still largely speculative, and much more research is needed to establish efficacy and safety. But the principle that sleep can be actively engaged as a partner in learning rather than passively accepted as a necessary rest period represents a shift in how we think about education and skill development. The relationship between sleep and learning creates a positive feedback loop. Learning produces changes in the brain that require consolidation during sleep. The depth and quality of sleep are enhanced by prior learning, with the brain seeming to sense when additional consolidation time is needed. And the improved memory and performance that result from good sleep enable more effective learning during subsequent waking periods. Conversely, when sleep is disrupted or insufficient, this positive cycle breaks down. Learning suffers not only because memories aren't consolidated, but also because the capacity for new learning is reduced. The hippocampus becomes less responsive to new experiences. Attention and working memory, both crucial for encoding information in the first place, are impaired. And the emotional regulation problems that accompany sleep loss can create a motivational barrier to learning, as stressed, irritable, or anxious individuals are less likely to engage effectively with new material. Understanding the role of sleep in learning has important implications for education. The traditional school day, starting early in the morning, despite teenagers' delayed circadian rhythms, may be working against the biological needs of adolescent brains. Later, school start times have been shown in multiple studies to improve academic performance, not just by reducing sleepiness during class, but by providing adolescents with the sleep they need for effective memory consolidation. Similarly, the phenomenon of distributed practice, the finding that learning sessions spaced out over time are more effective than massed practice, may partly reflect the benefits of intervening sleep. When you study the same material over several days, you get multiple opportunities for sleep-dependent consolidation between study sessions. This repeated consolidation, with each sleep period strengthening and integrating what was learned during the preceding day, leads to more robust and flexible knowledge than cramming everything into a single marathon session. For adults, the implications are equally important. In a knowledge economy where continuous learning is necessary throughout the career span, understanding how to leverage sleep for learning efficiency becomes a practical skill. The professional who pulls all-nighters to meet deadlines, or the parent who sacrifices sleep to find more hours in the day, is not just becoming tired. They're undermining their brain's ability to consolidate and retain new information, to solve problems creatively, and to adapt to changing circumstances. The study of sleep and learning has also revealed individual differences that are only beginning to be understood. Some people are naturally better at consolidating memories during sleep than others. Some show stronger sleep spindles, others more robust slow-wave activity. These differences may partly explain why some people are naturally better at learning certain types of material or skills. They may also suggest personalized approaches to optimizing learning, where individuals discover which types of study schedules, which times of day for learning, and which sleep habits work best for their own brain's peculiarities. As neuroscience advances and our ability to monitor and manipulate sleep becomes more sophisticated, the future may hold opportunities to enhance learning through sleep interventions. But even without high-tech interventions, the message from current research is clear. Sleep is not optional for learning. It's not time stolen from productivity, but time spent on one of the most important forms of cognitive processing your brain performs. Respecting your brain's need for sleep is respecting its need to learn, to remember, and to grow. The master clock, circadian rhythms. Deep within your brain, nestled just above where your optic nerves cross, lies a cluster of about 20,000 neurons, no larger than a grain of rice. This tiny structure, the suprachiasmatic nucleus, is your body's master clock, the conductor orchestrating the daily rhythms of nearly every cell and organ system in your body. Life on Earth evolved under the reliable cycle of day and night, created by our planet's rotation. This 24-hour rhythm has been such a constant feature of our environment for so long that virtually all organisms, from single-celled bacteria to humans, have evolved internal biological clocks that anticipate and adapt to it. These clocks don't simply respond to external light and darkness. They're true oscillators, capable of maintaining roughly 24-hour rhythms, even in the complete absence of external time cues. In mammals, the suprachiasmatic nucleus is the master pacemaker that coordinates these rhythms. Individual cells throughout your body, in your liver, heart, kidneys, and other organs, contain their own molecular clocks. But without coordination from the suprachiasmatic nucleus, these peripheral clocks would drift out of phase with each other, creating chaos in your physiology. The suprachiasmatic nucleus keeps them synchronized, functioning as the conductor of a vast physiological orchestra. The clock mechanism within each cell of the suprachiasmatic nucleus is elegantly simple in principle, though complex in detail. It involves a transcription-translation feedback loop, a molecular cycle that takes about 24 hours to complete. Clock genes are transcribed into messenger RNA, which is then translated into clock proteins. These proteins accumulate, and when they reach high enough levels, they enter the nucleus and suppress their own genes, shutting down production. As the proteins degrade over time, the suppression is released, transcription begins again, and the cycle continues. The key genes in this molecular clockwork include clock and BML01, which encode proteins that activate transcription of other clock genes, called period and cryptochrome. The period and cryptochrome proteins, once produced in sufficient quantities, form complexes that inhibit clock and BML1, creating the negative feedback loop. The timing of this loop, the period it takes to complete one cycle, is determined by various regulatory mechanisms, including phosphorylation, the addition of phosphate groups to proteins that can alter their stability and activity. This molecular clock operates in virtually every cell in your body, not just in the suprachiasmatic nucleus. What makes the suprachiasmatic nucleus special is its ability to receive information about environmental light and to synchronize both its own cellular clocks and the clocks in other parts of the brain and body to the external day-night cycle. Light is the primary time cue, or Zeitgeber, for the circadian system. Specialized photosensitive ganglion cells in your retina, distinct from the rods and cones responsible for visual perception, detect light levels and send this information directly to the suprachiasmatic nucleus via the retinohypothalamic tract. These ganglion cells contain a photopigment called melanopsin that is maximally sensitive to blue light, which is abundant in daylight and increasingly in artificial lighting. When light strikes these cells, particularly in the early morning or evening, when light levels are changing, the signal travels to the suprachiasmatic nucleus and can shift the phase of the circadian clock. Morning light advances the clock, making you feel sleepy earlier that evening and wake earlier the next morning. Evening light delays the clock, making you want to stay up later and sleep in longer. Light during the biological night, when your circadian system expects darkness, can be particularly disruptive, confusing the clock about what time it is. This sensitivity to light is why jet lag is so disorienting. When you fly across multiple time zones, your internal clock is suddenly out of sync with the external environment. Your body thinks it's still operating on your home time zone. It takes several days for the suprachiasmatic nucleus to fully adjust to the new light-dark cycle. And during this adjustment period, you experience the characteristic symptoms of jet lag: poor sleep, daytime fatigue, difficulty concentrating, digestive issues, and general malaise. Shift workers face a similar challenge, though often more chronically. Working night shifts and trying to sleep during the day forces the body to operate against its circadian rhythms. The circadian system is attempting to promote wakefulness and activity during the day, when the shift worker is trying to sleep, and to promote sleep at night, when they need to be alert and working. Complete adaptation is difficult or impossible for most shift workers, leading to chronic circadian disruption that can have serious health consequences. The suprachiasmatic nucleus doesn't just respond to light, it also generates rhythms internally, even in the absence of external cues. If you were placed in an environment without any time indicators, no light-dark cycle, no clocks, no routines, your circadian rhythms would continue, though they'd gradually drift. For most people, the internal period is slightly longer than 24 hours, averaging about 24.5 hours. This is why we need daily light exposure to keep our clocks synchronized. Without it, we'd slowly drift later and later each day. From the suprachiasmatic nucleus, timing information spreads throughout the brain and body through multiple pathways. Some neurons from the suprachiasmatic nucleus project to the pineal gland, which produces melatonin. Melatonin is sometimes called the hormone of darkness because its production is suppressed by light and increases during the night. The rise in melatonin in the evening contributes to the feeling of sleepiness and helps initiate sleep. The timing of melatonin secretion is tightly controlled by the suprachiasmatic nucleus and serves as an internal signal of circadian phase. Other projections from the suprachiasmatic nucleus influence body temperature regulation, hormone secretion, feeding behavior, and arousal systems in the brain. Body temperature follows a circadian rhythm, typically reaching its lowest point in the early morning hours and its peak in the late afternoon or evening. This temperature rhythm is closely linked to sleep propensity. You tend to fall asleep when your core temperature is declining and wake up as it's rising. Cortisol, a stress hormone with many regulatory functions, also follows a strong circadian rhythm. Levels are typically highest in the early morning, helping to promote wakefulness and prepare the body for the day ahead. They decline throughout the day and reach their lowest point in the evening and early night. Disruption of this cortisol rhythm is associated with various health problems, including mood disorders, metabolic dysfunction, and impaired immune function. The circadian system doesn't just control sleep and wakefulness, it influences virtually every aspect of physiology. Cell division, DNA repair, immune function, digestive activity, cardiovascular function, all show circadian rhythms. These rhythms make sense from an adaptive perspective. Different physiological processes are best performed at different times of day. Digestive activity is most efficient when you're awake and likely to be eating. Cellular repair and immune function can be prioritized during sleep when energy isn't needed for activity. Coordinating these processes temporally allows the body to operate more efficiently. When circadian rhythms are disrupted, either through lifestyle factors like shift work and jet lag, or through genetic or neurological conditions that affect the clock mechanism, health consequences can be significant. Chronic circadian disruption has been linked to increased risk of obesity, diabetes, cardiovascular disease, mood disorders, including depression and bipolar disorder, and even certain cancers. The mechanisms underlying these associations are still being investigated, but they likely involve the widespread effects of circadian rhythms on metabolism, immune function, and cellular repair processes. The suprachiasmatic nucleus itself changes with age. In older adults, the neurons of the suprachiasmatic nucleus show reduced amplitude in their circadian rhythms, less robust cycling of clock genes, and decreased sensitivity to light. These changes may contribute to the sleep problems common in older adults, including difficulty falling asleep, frequent nighttime awakenings, and early morning waking. The circadian signal that promotes consolidated nighttime sleep and daytime wakefulness becomes weaker and less distinct. Understanding circadian rhythms has important implications for optimizing health and performance. Aligning your activities with your circadian rhythms, eating during the day when digestive function is optimal, exercising when body temperature and muscle function peak in the late afternoon, scheduling cognitively demanding tasks when alertness is highest can enhance both performance and well-being. Light management is a powerful tool for manipulating circadian rhythms. Seeking bright light, especially outdoor light, in the morning helps advance the circadian clock, making it easier to wake up early and feel alert during the day. Avoiding bright light, especially blue-enriched light from screens, in the evening helps preserve the natural rise in melatonin and promotes sleepiness at bedtime. For people with circadian rhythm disorders, like delayed sleep phase syndrome, where the internal clock is shifted late, strategically timed light exposure can help shift the clock to a more socially convenient phase. The discovery of the suprachiasmatic nucleus and the molecular mechanisms of circadian rhythms represents one of the great successes of neuroscience, recognized with a Nobel Prize in Physiology or Medicine in 2017. What began as observations of daily rhythms in plants and animals has become a detailed understanding of how a small cluster of neurons coordinates the timing of physiology throughout the body, and how this system can be influenced by environment and behavior. Yet many questions remain. We still don't fully understand how the suprachiasmatic nucleus encodes information about seasonal changes, allowing organisms to adapt their physiology to different day lengths across the year. We're only beginning to understand how social cues, meal timing, exercise, and other non-light factors influence circadian rhythms. And we're still working to develop effective interventions for people whose circadian rhythms are disrupted by medical conditions, aging, or the demands of modern life. What's clear is that the circadian system is not a luxury, but a fundamental organizing principle of biology. Respecting your circadian rhythms, maintaining regular sleep-wake schedules, managing light exposure appropriately, is not just about avoiding grogginess. It's about allowing every cell and system in your body to operate at the right time, in coordination with every other system, creating the temporal organization that is essential to health. When sleep goes wrong, the human brain wasn't designed for sleep deprivation. Throughout most of our evolutionary history, the alternation of day and night, coupled with the vulnerabilities of darkness and the absence of artificial light, meant that sleeping at night was largely unavoidable. But modern life has changed this. Artificial lighting, shift work, global communication across time zones, the demands of career and family, and the allure of endless entertainment have created a culture where sleep is often sacrificed in favor of other activities. The consequences of this sacrifice are profound and far-reaching, affecting virtually every aspect of cognitive function. Even a single night of lost sleep creates measurable impairments in attention, work in memory, decision-making, and emotional regulation. Chronic sleep restriction, getting insufficient sleep, night after night, accumulates a sleep debt that produces cognitive deficits comparable to or worse than acute total sleep deprivation. The effects of sleep deprivation on memory are particularly well documented. Sleep deprivation before learning impairs the brain's ability to form new memories. The hippocampus, that crucial structure for memory encoding, shows decreased activity when you're sleep deprived. It's as though the neurons have become less responsive, less capable of forming the synaptic changes that represent new memories. Studies have shown that people who stay up all night before a learning task show approximately 40% reduction in the ability to form new memories compared to people who are well rested. But it's not just acute total sleep deprivation that causes problems. Chronic partial sleep restriction, getting, say, 6 hours of sleep per night when you need 8, also significantly impairs memory formation. What's particularly insidious about chronic sleep restriction is that people adapt subjectively. After a week or two of insufficient sleep, you may no longer feel as sleepy as you did initially. You adapt to the feeling of being tired, but objective measures of cognitive performance don't show this adaptation. Your memory, attention, and reaction time remain impaired even as you stop noticing how tired you are. Sleep deprivation after learning is equally problematic. If you learn something new and then don't sleep, or don't get adequate sleep, that information is less likely to consolidate into lasting memory. The neural replay that normally occurs during sleep is disrupted or prevented. The molecular processes that strengthen synaptic connections and integrate new memories with existing knowledge don't unfold properly. The result is that the fragile memory trace either fades or remains fragile, easily disrupted by interference from subsequent learning. At the molecular level, sleep deprivation causes widespread changes in the brain. Levels of brain-derived neurotrophic factor, crucial for synaptic plasticity and neuronal health, decline with sleep deprivation. Inflammatory markers increase. The balance of neurotransmitters shifts in ways that impair both synaptic plasticity and neural communication. Accumulated metabolic waste products that are normally cleared during sleep begin to build up, potentially contributing to the grogginess and cognitive impairment of sleep deprivation. One particularly concerning finding is that sleep deprivation appears to accelerate the accumulation of amyloid beta, a protein that forms plaques in the brains of Alzheimer's patients. Studies in both humans and animals have shown that even a single night without sleep leads to increased levels of amyloid beta in the brain. The glymphatic system, a waste clearance system in the brain that is particularly active during sleep, becomes less effective when sleep is disrupted. While it's too early to say definitively that chronic sleep deprivation causes Alzheimer's disease, the association is concerning and highlights that sleep deprivation isn't just about feeling tired. It may have long-term consequences for brain health. The cognitive effects of sleep deprivation extend beyond memory to virtually all aspects of thinking. Attention becomes impaired. You find it harder to focus on tasks, easier to be distracted. Response times slow. You become more likely to make errors, to miss important information, to fail to notice changes in your environment. Working memory, the ability to hold information in mind temporarily while manipulating it, declines significantly with sleep deprivation. Executive functions, the higher-level cognitive processes involved in planning, decision-making, impulse control, and flexible thinking, are particularly vulnerable to sleep loss. The prefrontal cortex, the brain region most responsible for executive function, shows some of the most pronounced changes with sleep deprivation. Brain imaging studies reveal decreased activity in prefrontal regions during cognitive tasks in sleep-deprived individuals. This prefrontal hypoactivity may explain why sleep-deprived people often make poor decisions, show impaired judgment, and struggle with tasks requiring sustained mental effort. The impairment isn't uniform across all types of cognitive tasks. Simple, well-practiced tasks may be relatively preserved, at least with mild sleep deprivation. But tasks requiring sustained attention, divided attention, creative thinking, or flexible problem-solving show marked impairment. Interestingly, some aspects of cognition may be more vulnerable in certain individuals. There appear to be genetic factors that influence how severely someone is affected by sleep deprivation. though everyone shows impairment with sufficient sleep loss. One of the most dangerous consequences of sleep deprivation is its effect on reaction time and vigilance. Drowsy driving is responsible for tens of thousands of accidents and hundreds of deaths each year. A driver who has been awake for 18 hours shows impairments in reaction time and judgment comparable to someone with a blood alcohol concentration of 0.05%, the legal limit in many jurisdictions. Being awake for 24 hours is equivalent to a blood alcohol concentration of 0.1%, clearly legally drunk. Yet people often don't recognize their own impairment. Sleep-deprived individuals consistently overestimate their performance on cognitive tasks. They feel they're doing reasonably well when objective measures show significant deficits. This disconnect between subjective experience and objective performance is particularly dangerous because it means people may take risks, attempting to drive or perform other critical tasks, not realizing how impaired they actually are. The emotional consequences of sleep deprivation are also significant. Sleep loss leads to increased irritability, mood swings, and emotional reactivity. The amygdala, the brain's emotional processing center, becomes hyperactive with sleep deprivation, while its connections to the prefrontal cortex, which normally helps regulate emotional responses, are weakened. This combination means that sleep-deprived people show exaggerated emotional reactions to negative stimuli and have difficulty regulating those reactions. Chronic sleep deprivation is strongly associated with mood disorders. People with insomnia are at significantly elevated risk of developing depression or anxiety disorders. Conversely, treating sleep problems can sometimes alleviate mood symptoms. The relationship appears to be bidirectional. Sleep problems can contribute to the development of mood disorders, and mood disorders can exacerbate sleep problems, creating a vicious cycle. The good news is that many of the cognitive effects of sleep deprivation are reversible with adequate recovery sleep. After a night or two of good sleep, cognitive performance generally returns to normal. However, recovery isn't instantaneous. Even after a full night of recovery sleep, some subtle deficits may persist, particularly if the sleep deprivation was severe or prolonged. And there's evidence that very chronic sleep restriction may have effects that don't fully reverse, even with extended recovery periods. The question of whether sleep debt can be made up on weekends is complex. While weekend recovery sleep can partially alleviate the acute cognitive effects of weekday sleep restriction, it doesn't fully compensate. The pattern of insufficient weekday sleep followed by excessive weekend sleep appears to cause its own problems, including disruption of circadian rhythms that can make Monday morning particularly difficult. The ideal situation is to maintain consistent, adequate sleep every night. For most adults, this means 7 to 9 hours of actual sleep, not just time in bed. Individual needs vary, and factors like age, health, activity level, and genetics all influence how much sleep someone needs. The best gauge is how you feel and function. If you're sleepy during the day, relying on caffeine to stay alert, struggling to concentrate, or finding yourself irritable and emotionally reactive, you're probably not getting enough sleep. Caffeine and other stimulants can temporarily mask some symptoms of sleep deprivation, improving alertness and attention. But they don't actually restore cognitive function to baseline. Stimulants can keep you awake and make you feel more alert, but they don't fix the underlying problems with memory consolidation, decision-making, and emotional regulation that sleep deprivation causes. And using stimulants, especially late in the day, can itself interfere with sleep, perpetuating the cycle of sleep deprivation. Understanding the cognitive costs of sleep deprivation has led to policy changes in some domains. Medical residency programs have implemented restrictions on work hours after research showed that sleep-deprived residents made more medical errors. Some transportation industries have regulations limiting consecutive hours of operation for pilots, truck drivers, and others in safety-sensitive positions. Schools have experimented with later start times for adolescents, recognizing that teenagers' delayed circadian rhythms make early morning classes particularly challenging. Yet, in many areas of life, sleep deprivation remains normalized or even celebrated. The executive who brags about functioning on 4 hours of sleep, the student who pulls all-nighters to finish assignments, the parent who sacrifices sleep to juggle work and family responsibilities, all are examples of how our culture often treats sleep as expendable. The research on cognitive consequences of sleep deprivation tells a different story. Sleep is not optional. It's not weakness or inefficiency to need sleep. It's biology, and ignoring that biology has real costs to our mental function, our health, and our well-being. The shadow side, nightmares and PTSD. Not all sleep is peaceful. For some people, closing their eyes and drifting into sleep means entering a landscape of terror, a world of nightmares that can feel more vivid and real than waking life. While everyone experiences occasional bad dreams, for people with nightmare disorder or post-traumatic stress disorder, nightmares are a chronic and debilitating problem that can dominate their sleep and spill over into waking hours. A nightmare is more than just an unpleasant dream. It's a vivid, intensely emotional dream that typically involves threats to survival, security, or physical integrity. Common nightmare themes include being chased or attacked, falling from great heights, being trapped or paralyzed, witnessing violence or death, or experiencing catastrophic events. The emotional response is usually fear or terror, though nightmares can also evoke other intense negative emotions, like sadness, anger, or disgust. Nightmares typically occur during REM sleep, when dreams are most vivid and elaborate. The heightened activity of the amygdala during REM, combined with reduced prefrontal control, creates conditions where emotional responses can become exaggerated. In a typical dream, even unpleasant situations may not trigger intense fear. But in a nightmare, the fear response is overwhelming and often results in awakening. When you wake from a nightmare, the transition back to waking consciousness can be gradual. You may remain fearful and disoriented for several minutes, your heart pounding, breathing rapid, body tense. The vivid imagery and emotions of the nightmare may persist, making it difficult to calm down and return to sleep. For people who have frequent nightmares, the anticipation of nightmares can itself become a source of anxiety, leading to sleep avoidance and insomnia. Occasional nightmares are common and normal. They occur more frequently during times of stress, after watching frightening movies or reading disturbing content, during illness or fever, and as a side effect of certain medications. Children have nightmares more frequently than adults, which may reflect their still developing emotional regulation abilities, or their inexperience with processing frightening experiences. But when nightmares become frequent, causing significant distress and interfering with sleep quality or daily functioning, they meet the criteria for nightmare disorder. This condition affects roughly 2 to 8% of the general population. It's more common in people with anxiety disorders, in people who have experienced trauma, and in those with certain psychiatric or neurological conditions. The most severe and intractable nightmares occur in the context of post-traumatic stress disorder, or PTSD. PTSD develops in some people after experiencing or witnessing a traumatic event, such as combat, sexual assault, severe accidents, natural disasters, or violent crime. Not everyone who experiences trauma develops PTSD. Many people show resilience, experiencing initial distress that gradually resolves. But for those who do develop PTSD, nightmares are one of the hallmark symptoms. PTSD nightmares have some distinctive characteristics. About half of them directly replay the traumatic event, sometimes with dreamlike distortions, but recognizably reenacting what happened. These replicative nightmares can be extraordinarily distressing, forcing the person to relive their worst moments repeatedly. The other half of PTSD nightmares don't directly replay the trauma, but feature similar themes, threats, or emotional tones. A combat veteran might not dream of the specific firefight that caused their trauma, but might dream of other dangerous situations involving violence and threat. The frequency of nightmares in PTSD is striking. While someone without PTSD might have a nightmare a few times per year, people with PTSD often have nightmares multiple times per week or even every night. Some experience several nightmares in a single night. This chronic nightmare activity severely disrupts sleep, leading to chronic sleep deprivation that exacerbates other PTSD symptoms, including hypervigilance, irritability, difficulty concentrating, and emotional dysregulation. The neurobiological mechanisms underlying nightmares, particularly PTSD nightmares, are beginning to be understood. The amygdala, which processes fear and other emotions, appears to be hyperactive in people with PTSD. This hyperactivity persists during sleep and may contribute to the generation of fear-themed dream content. The prefrontal cortex, which normally helps regulate emotional responses and provides context that can dampen fear reactions, shows reduced activity in PTSD, both during waking and potentially during sleep. Memory processing during sleep is also disrupted in PTSD. Normally, REM sleep is thought to help integrate emotional experiences and reduce their emotional charge through a process of emotional memory consolidation. The traumatic memory is reactivated, but in a neurochemical environment free of noradrenaline, the primary stress hormone. This reactivation without stress may help decouple the memory from its intense emotional response, allowing the person to remember what happened without being overwhelmed by emotion. But in PTSD, this process appears to malfunction. Noradrenaline levels may be abnormally elevated even during REM sleep. The traumatic memory gets reactivated during sleep, possibly appearing as nightmare content. But instead of being desensitized, it may be re-traumatizing. Each nightmare may reinforce the fear response rather than diminishing it. This could explain why PTSD nightmares are so persistent, and why people with PTSD often feel that their symptoms are getting worse rather than better with time. Treatment of PTSD nightmares has advanced considerably in recent years, moving beyond simply treating insomnia or suppressing REM sleep. Image rehearsal therapy has emerged as the most effective psychological treatment specifically for nightmares. In IRT, the person recalls a recurring nightmare in detail while awake. They then rewrite the nightmare, changing the narrative in any way they choose. They might change the ending to one that's more positive or empowering. They might insert protective figures or elements into the dream. They might alter threatening figures to make them less frightening. The revised dream script is then rehearsed mentally during the day, repeatedly imagining the new version. The goal is to overwrite the nightmare with an alternative narrative. IRT doesn't erase the traumatic memory or even necessarily change the content of the first part of the dream. But by providing an alternative ending or resolution, it may change the emotional trajectory of the dream and reduce the likelihood of awakening in terror. IRT has been shown in multiple studies to reduce nightmare frequency and intensity. It can be delivered in individual or group settings, and benefits often appear within a few weeks. The exact mechanisms by which IRT works are still being investigated. It may involve reconsolidation of memory, the process by which memories can be modified when they're reactivated. Or it may simply provide a sense of control and agency that carries over into dreams. Other therapeutic approaches for PTSD nightmares include exposure, relaxation, and re-scripting therapy, which combines elements of IRT with exposure therapy and systematic desensitization. Lucid dreaming therapy, teaching people to recognize when they're dreaming and to exert some control over dream content, has also shown promise in some studies, though it remains somewhat experimental. Medications can be helpful for PTSD nightmares, though they're generally considered a second-line treatment after psychotherapy. Prazosin, a medication originally developed for high blood pressure, has been widely used for PTSD nightmares. It works by blocking noradrenaline receptors, potentially restoring the noradrenaline-free environment during REM sleep that's thought to be necessary for healthy emotional memory processing. Some studies have found prazosin effective at reducing nightmare frequency and improving sleep quality, though results have been mixed. Other medications, including certain antidepressants and atypical antipsychotics, have also been used, often in combination with psychotherapy. The choice of medication depends on individual factors, including other PTSD symptoms, co-occurring conditions like depression or anxiety, and potential side effects. Beyond specific treatments, general sleep hygiene is important for managing nightmares. Maintaining regular sleep schedules, creating a comfortable and safe sleep environment, avoiding alcohol and recreational drugs, which can disrupt sleep architecture, and managing stress through various techniques can all help improve overall sleep quality and potentially reduce nightmare frequency. For children with nightmares, parental reassurance and comfort are important. Most childhood nightmares don't require specific treatment beyond helping the child feel safe and gradually calm down after waking. But if nightmares are frequent, very distressing, or associated with trauma or other psychological issues, professional help may be needed. The impact of chronic nightmares extends beyond disrupted sleep. People with frequent nightmares often develop a fear of sleep itself, engaging in sleep avoidance behaviors that worsen insomnia. They may experience shame or embarrassment about their nightmares, especially if the content is bizarre or personally disturbing. In relationships, nightmares can be disruptive, particularly if the person cries out, thrashes, or wakes their partner. For people with PTSD, nightmares are often one of the symptoms that persists longest, sometimes continuing long after other PTSD symptoms have improved with treatment. This persistence highlights the importance of directly addressing nightmares, rather than assuming they'll resolve when other symptoms improve. Effective nightmare treatment can significantly improve quality of life, not just by improving sleep, but by reducing the sense of being haunted by trauma, of having the past intrude unbidden into the present. Understanding nightmares as a sleep disorder, as a treatable condition, rather than an inevitable consequence of trauma or simply bad luck, has been an important shift in how mental health professionals approach these distressing experiences. While we may never fully eliminate nightmares, we now have tools to reduce their frequency and intensity, to help people reclaim their sleep and their sense of safety in the night. Lucid dreaming, consciousness in sleep. Imagine being in the middle of a vivid dream, perhaps flying over landscapes or engaged in an impossible adventure, when suddenly you realize this is a dream. With that realization, everything changes. You're still dreaming, still experiencing the rich perceptual world of the dream, but now you know it's a dream. You're conscious within the dream. This is lucid dreaming, and it represents one of the most fascinating frontiers in the study of consciousness. Lucid dreaming is the experience of being aware that you're dreaming while the dream is still unfolding. This awareness exists on a continuum. At the lowest level, you might have a fleeting thought that something seems dreamlike before the dream carries on, and you forget. At the highest level, you might have complete clarity that you're dreaming, full memory of your waking life, and the ability to make conscious decisions about what to do in the dream. The prevalence of lucid dreaming varies widely. Most people report having experienced at least one lucid dream in their lifetime. Some people have them frequently, even multiple times per week, while others rarely or never experience them. Childhood appears to be a time when lucid dreams are more common, perhaps related to the greater amounts of REM sleep children experience, or to developmental factors in consciousness. The term lucid dream was coined by Frederick Van Eden in 1913, though descriptions of dream awareness go back much further. In ancient texts, including Greek philosophy and Tibetan Buddhism, we find references to knowing one is dreaming. In Tibetan dream yoga, cultivating awareness during dreams is considered a spiritual practice, a way to recognize the dreamlike nature of waking experience, and to practice maintaining awareness through different states of consciousness, including death. Modern scientific study of lucid dreaming began in earnest in the 1980s with the pioneering work of Stephen LaBerge at Stanford University. LaBerge developed a method for lucid dreamers to signal to researchers that they were lucid. Before going to get sleep, a lucid dreamer would agree to make a specific pattern of eye movements, like moving their eyes left, right, in rapid succession, once they became lucid in a dream. Since eye muscles are not paralyzed during REM sleep, these eye movements could be detected by researchers monitoring the sleeper's brain activity and eye movements. When dreamers successfully sent these signals, brain recordings confirmed they were in REM sleep, not awake. But their EEG patterns during lucid REM sleep showed some differences from non-lucid REM sleep. This established beyond doubt that lucid dreaming is a genuine phenomenon, a distinct state of consciousness occurring during sleep, not a brief awakening or a false memory of dreaming. The neuroscience of lucid dreaming has revealed fascinating insights into how consciousness works. During ordinary REM sleep, the prefrontal cortex, particularly the the dorsolateral prefrontal cortex, shows reduced activity compared to waking. This region is crucial for self-awareness, metacognition, working memory, and executive control. Its deactivation during REM may explain why we typically don't question the bizarre logic of dreams, why we accept impossible events as normal, and why we have limited or no access to our waking memories and identity. But during lucid REM sleep, prefrontal activity increases. Brain imaging and EEG studies have shown that lucid dreaming is associated with increased activity in prefrontal regions and with increased connectivity between prefrontal cortex and other brain regions. Essentially, lucid dreaming appears to be a hybrid state where some aspects of waking consciousness, particularly self-awareness and reflective thought, are reactivated within the REM sleep state. This prefrontal reactivation is not complete. Even in lucid dreams, prefrontal function doesn't return to full waking levels. This may explain why lucid dreamers, while aware they're dreaming, sometimes still struggle with logical thinking or maintaining consistent goals. The dream environment can still capture attention and lead the dreamer away from their intended actions. Interestingly, lucid dreaming also shows increased activity in the parietal cortex, regions involved in spatial awareness and sense of agency. And there's evidence of increased gamma band activity, brain oscillations in the 30 to 100 Hz range that are associated with conscious awareness and attention. During lucid dreams, gamma activity is enhanced compared to non-lucid REM sleep, particularly in frontal regions. The question of how to induce lucid dreams has practical importance, both for research and for people who want to experience them. While some people seem to lucid dream naturally without effort, various techniques can increase the likelihood of lucidity. Reality testing is one commonly recommended approach. Throughout the day, you ask yourself whether you're dreaming and perform a simple test, like trying to push your finger through your palm or looking at text, looking away, and checking if it changed. The idea is that if you make reality testing a habit during waking, you'll eventually do it during a dream. And when you do, the reality test will fail in the dream. Perhaps your finger will pass through your palm, revealing that you're dreaming. Mnemonic induction of lucid dreams, or MILD, is a technique developed by Stephen LaBerge. As you're falling asleep, you repeatedly tell yourself that you will recognize when you're dreaming. You imagine yourself back in a recent dream, but this time noticing something that reveals it's a dream and becoming lucid. This intention setting and mental rehearsal appears to increase the likelihood of lucidity. Wake back to bed methods involve setting an alarm to wake yourself after about 5 or 6 hours of sleep, staying awake briefly, then going back to sleep with the intention of having a lucid dream. Since REM periods are longer and more intense in the later part of the night, and since briefly waking and then returning to REM may increase prefrontal activation, this technique can be effective. For some people, certain supplements may enhance the likelihood of lucid dreaming. Galantamine, a medication used for Alzheimer's disease that increases acetylcholine levels in the brain, has been shown in studies to increase lucid dream frequency when taken in the middle of the night, along with wake back to bed techniques. The mechanism may involve enhancing REM sleep and increasing the likelihood of consciousness during REM. Once lucidity is achieved, maintaining it can be challenging. The excitement of realizing you're dreaming can cause awakening. the dream environment can become unstable, with objects morphing or the dream scene dissolving. Experienced lucid dreamers develop techniques for stabilizing the dream, like spinning or rubbing their hands together, or repeatedly reminding themselves that they're dreaming. The question of control in lucid dreams is subtle. Lucidity, awareness that you're dreaming, doesn't automatically confer complete control over the dream. Some lucid dreamers find they can exert considerable control, creating or transforming objects, flying, changing scenes at will. Others find that while they know they're dreaming, the dream still largely unfolds on its own, though they can make choices about how to respond. This variability in control has led some researchers and lucid dream practitioners to distinguish between lucidity, the awareness of dreaming, and control, the ability to intentionally alter dream content. The two often go together, but not always. Some non-lucid dreams show elements of control, where the dreamer directs the narrative without explicitly recognizing they're dreaming. And some lucid dreams involve clear awareness but limited control. The potential applications of lucid dreaming have attracted considerable interest. For people with recurring nightmares, learning to become lucid during nightmares could allow them to transform the nightmare into something less threatening, or to escape it by intentionally waking themselves. Some studies have found that lucid dreaming therapy can be effective for nightmare disorder, though more research is needed. For creative pursuits, lucid dreaming might offer a unique problem-solving environment. Some artists, writers, and inventors report having used lucid dreams for creative inspiration or to practice and refine artistic skills. The dream environment, freed from physical constraints, might allow for exploration that isn't possible while awake. Athletes and musicians have experimented with using lucid dreams for mental rehearsal of skills. Since the brain regions controlling movement are active during dreams of movement, mentally practicing a skill in a lucid dream might engage similar neural circuits as actual practice. Some research suggests that mental practice during lucid dreams can improve performance, though it's unclear whether this offers advantages over mental practice while awake. From a scientific perspective, lucid dreaming offers a remarkable tool for studying consciousness. It allows researchers to ask questions about the relationship between brain activity and subjective experience in ways that aren't possible otherwise. For instance, researchers can ask lucid dreamers to perform specific mental tasks during the dream, like singing or doing arithmetic, and observe what brain regions become active. This can reveal how different aspects of conscious experience map onto brain function. Lucid dreaming has also been used to study the relationship between perception and imagination. In waking life, these are usually clearly distinct, but in lucid dreams, the boundary blurs. You're imagining the dream content in some sense, since it's internally generated, but it feels perceptual, as vivid and real as seeing, hearing, and feeling in waking life. Understanding how the brain creates perceptual experiences from purely internal activity, without external sensory input, could shed light on the nature of perception and consciousness. The ethical and philosophical implications of lucid dreaming are intriguing. If you're conscious and making decisions during lucid dreams, are those dreams subject to moral evaluation in the same way waking actions are? Most would say no, since dream actions don't affect others in the real world. But the question becomes interesting in edge cases. Could recurrent violent or harmful lucid dream scenarios, even knowing their dreams, affect someone's psychology or desensitize them to violence? There's also the question of whether lucid dreaming affects sleep quality. Some worry that maintaining consciousness during sleep might interfere with the restorative functions of sleep or reduce sleep quality. However, research so far hasn't found evidence of harm. Lucid dreamers don't appear to have poorer sleep or more daytime sleepiness than non-lucid dreamers. Still, there are some who caution against pursuing lucid dreaming too intensively, particularly using techniques that involve sleep interruption, since disrupting natural sleep could have costs. For most people, occasional lucid dreams are a benign and often enjoyable phenomenon. They offer a glimpse into the remarkable flexibility of consciousness, the brain's ability to create rich, immersive experiential worlds, and the possibility of awareness during a state, sleep, that we usually think of as unconscious. They remind us that consciousness is not simply on or off, but comes in degrees and varieties that we're only beginning to understand. As research continues, we may learn more about how to reliably induce lucid dreams. What factors determine the degree of lucidity and control someone can achieve? And whether lucid dreaming has practical applications beyond the intrinsic interest of the experience itself. We may also learn more about what lucid dreaming can teach us about consciousness, about the relationship between brain states and subjective experience, and about the remarkable creative and simulative capacities of the sleeping mind. Conclusion. As you drift towards sleep tonight, your brain is preparing for a journey far more active and purposeful than simple rest. The rhythms of your sleep will carry you through stages of deep restoration, periods of vivid dreaming, and moments of neural housekeeping that are essential for tomorrow's alertness and learning. Your hippocampus will replay the day's experiences, transferring memories from temporary storage to more permanent form. Your neurons will strengthen some connections while pruning others, sculpting the networks that represent your knowledge and skills. Your glymphatic system will clear metabolic wastes that accumulated during waking hours. And through it all, your master clock in the suprachiasmatic nucleus will keep time, coordinating these processes with the external cycle of day and night. The sleeping mind is not idle. It's working, learning, consolidating, creating, and preparing. Dreams, those strange amalgams of memory, emotion, and imagination, may be helping you process experiences, solve problems, or maintain the flexibility of your thinking. Nightmares, when they occur, though distressing, may reflect the brain's attempts to work through difficult emotions or threatening scenarios. And for those fortunate enough to experience it, lucid dreaming offers a window into a hybrid state of consciousness, where awareness persists even as the dream unfolds. Yet despite centuries of study and recent advances in neuroscience, sleep and dreams remain in many ways mysterious. We understand much about the mechanisms, the brain regions involved, the molecular processes, the relationships to memory and learning. But we still struggle with deeper questions. Why did consciousness evolve to have this remarkable capacity to create immersive experiential realities each night? Why do we need to spend so much of our lives in a state of apparent vulnerability? What is the relationship between the sleeping mind and the waking self? These questions may never have complete answers, but the search for understanding continues to reveal how intricately sleep is woven into every aspect of our biology and psychology. Far from being wasted time, sleep is an active, essential state that enables us to learn, to remember, to regulate our emotions, to maintain our health, and perhaps to understand ourselves in ways we don't fully appreciate. As research advances, we're moving toward a future where we may be able to better optimize sleep for learning and memory, treat sleep and dream disorders more effectively, and perhaps even harness the sleeping mind's capacities in new ways. But even now, the most important takeaway is simple. Sleep matters. It's not optional, not a luxury, not time that could be better spent being productive. It's a fundamental biological necessity, as important as food or water, essential to everything we do and everything we are. So tonight, as you prepare for sleep, perhaps you'll appreciate the complexity and wonder of what's about to unfold. The quiet, the darkness, the gradual relaxation into unconsciousness. These aren't just the absence of waking. They're the beginning of a different kind of work, a different kind of experience, no less important than anything you do during the day. Your sleeping mind is about to embark on its nightly journey through stages and cycles, consolidating what you learned, processing what you felt, preparing you for tomorrow's challenges. If you've enjoyed exploring the mysteries of sleep, dreams, and memory tonight, please consider liking this video and subscribing to Bedtime Biology for more gentle explorations of the natural world. Share your thoughts in the comments below. Where are you watching from? Do you remember your dreams? Have you ever experienced a lucid dream? What questions do you still have about the sleeping mind? Until next time, sleep well, dream deeply, and let your mind do its remarkable work. Your brain knows what it needs. Give it the time and respect it deserves. Good night and sweet dreams.